Current electricity. Electricity is an important source of energy in our everyday life. In this chapter, we shall study current electricity, that is charge in motion. Charges in motion constitute an electric current. When two bodies at different electric potentials are connected by a metallic wire, electrons flow from the body at lower potential to the one at higher potential. This flow of charges is electric current. Electric current. The electric current is the rate of flow of charges. SI unit of current is ampere. When 1 coulomb of charge flow through a conductor in 1 second, the current flowing is said to be 1 ampere. Ohm's law. The relation between current through a conductor and applied potential difference is given by Ohm's law. Statement. As long as physical state, that is material, dimensions and temperature of a conductor remains the same, the electric current flowing through a given conductor is directly proportional to the potential difference applied across it. That is, V is proportional to I. V upon I is equal to R, where R is constant of proportionality. The graph of I versus V across conductor is a straight line as shown in figure. R represents the opposition to flow of current and is known as resistance. SI unit of resistance is ohms. Reciprocal of resistance is called conductance. SI unit of conductance is Siemens, denoted by S. Limitations of Ohm's law. Materials like copper, aluminium or silver obey Ohm's law, hence they are called as ohmic conductors. For such materials, the graph of current against voltage is a straight line and value of resistance is constant. There are certain materials which do not obey Ohm's law. These materials are called non-ohmic conductors. Non-ohmic conductors have non-linear current-voltage relationship. For such materials, the graph of the current against voltage is not a straight line. One common semiconducting device that has non-linear characteristic is a diode. Specific resistance, that is resistivity. The resistance R of a conductor is directly proportional to its length L and is inversely proportional to its area of cross section A. Hence, R is proportional to L and R is proportional to 1 upon A, that is R proportional to L upon A, or R equal to rho L upon A, where rho is constant of proportionality and is called as specific resistance or resistivity of conductor. Rho equal to RA upon L. SI unit of rho is ohm meters. Specific resistance is defined as the resistance per unit length per unit area of cross section of wire. Resistivity is a physical property of material. Reciprocal of the resistivity is called conductivity of the material. Sigma equal to 1 upon rho. SI unit of sigma is Siemens per meter. Depending upon resistivity, the materials are classified as first, conductors, second, insulators, third, semiconductors. Temperature dependence of resistance. The resistance of any material depends on its temperature. For metals, it is found that the resistance increases with temperature. Temperature coefficient of resistance alpha. It is defined as the increase in resistance per unit original resistance at 0 degrees Celsius per degree rise in temperature. Alpha equal to RT minus R0 divided by R0 into T, where R0 is resistance of conductor at 0 degrees Celsius. RT is resistance of conductor at T degrees Celsius. Thus, RT minus R0 is increase in resistance. SI unit of temperature coefficient of resistance alpha is per degree Celsius. A graph of resistance against temperature is a straight line. Therefore, any metal has a constant and positive temperature coefficient of resistance. The temperature coefficients of some metallic alloys are very small compared to those of the pure metals. For example, manganese, an alloy of 84% copper, 12% manganese, 4% nickel, and constantan, an alloy of 60% copper and 40% nickel. Due to very small temperature coefficient of resistance, manganese and constantan are used in high quality resistance boxes. Thermistor. Thermistor is temperature sensitive semiconductor device. Its resistance changes very rapidly with change in temperature. That is, thermistors have large temperature coefficient of resistance. There are two types of thermistors. First, PTC, positive temperature coefficient. Second, NTC, negative temperature coefficient. The resistance of PTC thermistors increase non-linearly with temperature, and resistance of NTC thermistors decrease non-linearly with temperature as shown in figure. Uses of thermistor. Thermistors are used as temperature sensors. Thermistors are used in digital thermometer. Thermistors are used in automatic temperature control systems. Thermistors are used in remote temperature sensing. Thermistors are used in voltage stabilizer. Thermistors are used in protection of motor windings. Superconductivity. We know that resistivity of material depends on temperature. For some metals and alloys, resistivity suddenly becomes zero at a particular low temperature. This temperature is called critical temperature, TC. For example, resistance of mercury falls to 0 ohms at 4.2 degree Kelvin. Superconductivity, the phenomenon of losing resistivity completely at a particular temperature, that is critical temperature, is called superconductivity. Superconductivity has lots of applications. Rather, it will change our life to a great extent. The only problem is that superconductivity exists at sub-zero temperature, that is at negative temperature in degrees Celsius. That is why the scientists all over the world are trying hard to obtain superconductivity at normal room temperature. Color code for resistors. Resistor is an important component of electric circuits. We use resistors to limit current through a particular path of the circuit. Resistances available in market are mainly of two types. First, wire wound resistors. Second, carbon resistors. Higher range resistors are mostly carbon resistors. They are small and inexpensive. Since carbon resistors are small in size, their values are color coded to mark their values in ohms. The color coding is standardized by Electronic Industries Association, EIA. The color code scheme for resistors is given in the following table. Figure shows color coded resistor. The value of R is printed in the form of color rings. On one side there is tolerance ring, which is either golden or silver. Start observing other side. First two color rings give first two digits of value, and third ring indicates the decimal multiplier. In case tolerance ring is absent, the color rings lie closer to one terminal. Then start observing from that side. For example, if the code for the resistor is orange, white, red, golden, value of resistance is 39 into 10 raised to 2 ohms with tolerance plus minus 5%. EMF and potential difference. We use electric cell as source of electric energy. When a conductor is connected across a cell, electrons flow from the negative terminal of the cell to the positive terminal through the external conductor. EMF, electromotive force. The energy supplied by the cell to circulate unit charge once around the circuit is called EMF of the cell. EMF equal to work done upon charge. EMF is measured in volt. Potential difference. The energy spent by source of EMF in circulating unit charge through external resistance is called potential difference of the cell. Ohm's law applied to complete circuit. We use a source of electricity for sending current through the external circuit of the total energy E developed by the source. A part VR is used by the source itself to overcome its internal resistance, and only the remaining part V is available to send the current in the external circuit. Thus, terminal potential difference can be considered as the useful part of EMF. E equal to V plus VR. By Ohm's law, V equal to IR, VR equal to I into small r. Therefore, E equal to IR plus I into small r, that is equal to I into bracket capital R plus small r. Therefore, I equal to E upon capital R plus small r. EMF equal to potential difference minus I into small r. When circuit is open, I equal to 0, hence V equal to E. When R equal to 0, then V equal to E. In all the other cases, E is greater than V. Work done by electric current. When an electric current is passed through a conductor, it becomes hot, that is, heat is generated. This is heating effect of electric current. Joule's law. The quantity of heat generated in a resistor of resistance R when a current I flows through it for a time t is directly proportional to first, square of current, second, resistance of resistor, third, time for which current flows. Thus, H is proportional to I square RT. If heat H is measured in joules, then H is equal to I square RT joules. If heat H is measured in calorie, then H is equal to I square RT upon 4.18 calorie. Power in electric circuit. Electric power. The rate at which electrical work is done or the rate at which electrical energy is consumed in the circuit is called electric power. Power is equal to work upon time. Power is measured in watt. 1 watt equal to 1 joule upon 1 second. 1 kilowatt equal to 10 raised to 3 watt. 1 horsepower equal to 746 watt. Electric power equal to electrical energy consumed upon time. Thus, electrical energy consumed is equal to power into time. Therefore, W is equal to P into T. If power is measured in kilowatt and time is expressed in hour, the electrical energy is expressed in kilowatt hour kWh. The energy meter fixed in every house records the consumed energy in units, each unit equal to 1 kilowatt hour. 1 kWh equal to 1 kilowatt into 1 hour equal to 1000 watt into 3600 seconds equal to 3.6 into 10 raised to 6 joules. It must be remembered that watt and kilowatt are units of power. Kilowatt hour is unit of energy. For domestic uses, electrical energy is supplied to us by the State Electricity Board. The electric meters fixed in our homes record the electrical energy consumed by us in terms of kilowatt hours. We are charged electricity bills according to the number of kilowatt hours of electrical energy consumed by us.